Every few months, somewhere along the restless edges of Earth's tectonic plates, an earthquake reminds humanity that the planet is never truly at rest. Most arrive with little warning. Some shake only remote stretches of ocean. Others leave scars across cities and coastlines. A few become milestones that scientists return to for decades because they reveal something new about the immense forces constantly reshaping the surface of our world. Then there are the earthquakes that raise deeper questions. Why do some sections of a subduction zone rupture while neighbouring sections remain silent? Why does one earthquake produce only a modest tsunami, while another of similar location unleashes waves that travel across entire oceans? Why do aftershocks sometimes cluster directly over the rupture, yet in other cases migrate toward its edges? And perhaps the most important question of all, when one locked section finally breaks, what does it reveal about the portions that remain locked? Those questions came sharply back into focus on the 17th of July, 2026. At 14 hours, 48 minutes and 39 seconds Coordinated Universal Time, seismic instruments across the world detected powerful waves radiating outward from the Pacific Ocean off the coast of Chiapas, Mexico. Within minutes, automated systems calculated a large earthquake approximately 36 miles or 58 kilometers west-southwest of Puerto Madero. The initial estimates changed slightly as more seismic stations reported their data, but the conclusion remained the same. A major earthquake had struck one of the most active plate boundaries on Earth. The final magnitude settled at 7.3. Its depth was estimated at approximately 11.5 miles, or 18.6 kilometers, while detailed analyses suggested that the actual rupture on the plate boundary occurred even shallower, at roughly 9 miles or 15 kilometers below the sea floor. That distinction may appear minor, yet for geophysicists it carries enormous importance. A shallow rupture behaves very differently from a deeper one. It transfers energy more efficiently toward the surface, produces stronger coastal shaking, and has a greater chance of vertically displacing the sea floor. Even a relatively small amount of vertical movement across the ocean floor can disturb millions of tons of seawater, creating tsunami waves that spread outward from the source. Fortunately, this event did not grow into one of the colossal magnitude 8 or magnitude 9 earthquakes capable of sending destructive tsunamis across the Pacific. Instead, observations showed a relatively modest regional tsunami, exactly the kind scientists would expect from a shallow magnitude 7.3 megathrust rupture with a limited rupture length and moderate fault slip. Yet the earthquake was significant for another reason. It became the 9th earthquake of magnitude 7 or greater recorded worldwide during the year 2026 through the 20th of July, according to the United States Geological Survey Earthquake Catalogue. On its own, that number might not appear remarkable. Earth does not release tectonic energy, according to a predictable annual schedule. Some years produce nearly 20 major earthquakes. Others produce fewer than 10. Still, when viewed alongside the past decade, an interesting pattern begins to emerge. During 2016, the world recorded 16 earthquakes of magnitude 7 or greater. The following year experienced a notable decline, with only 7 such earthquakes, making it the quietest year of the past decade in terms of large seismic events. Activity increased dramatically during 2018, when 17 earthquakes exceeded magnitude 7. 2019 saw 10. 2020 recorded 9. Then activity surged once more. Both 2021 and 2023 each produced 19 earthquakes of magnitude 7 or greater, tying for the highest annual total over the decade. 2022 recorded 11. 2024 returned to 10. 2025 finished with 9 major earthquakes, despite producing one of the most powerful earthquakes of the decade, proving that the number of large earthquakes says little about the size of the largest event in any given year. By the 20th of July in 2026, the count had already reached 9. For seismologists, those numbers carry an important lesson. Earth is not speeding towards some inevitable increase in earthquakes, nor is it becoming unusually quiet. Instead, tectonic stress accumulates independently along hundreds of plate boundaries around the globe. Each fault stores energy according to its own geological history. The annual total simply reflects when different faults finally reach their breaking point. One year may witness numerous magnitude 7 earthquakes scattered across unrelated plate boundaries. Another may experience fewer earthquakes, but include a single giant megathrust that releases hundreds of times more energy than all the others combined. The Chiapas earthquake belongs to that global sequence, yet its origin lies within a tectonic setting that has fascinated geologists for generations. Stretching along the Pacific margin of southern Mexico lies one of Earth's classic subduction zones. Far offshore, the Middle America Trench marks the boundary where the dense oceanic crust of the Cocos Plate dives beneath the lighter continental crust of the North American Plate. Farther southeast, this system gradually approaches the complex interaction with the Caribbean Plate, creating one of the most intricate plate junctions in the Western Hemisphere. Unlike transform faults, such as California's San Andreas Fault, where plates slide horizontally past one another, the Middle America Trench is dominated by compression. Here, one tectonic plate descends into Earth's mantle while another rides above it. The process has continued for millions of years, driven by the slow but relentless motion of Earth's lithosphere. That movement is almost impossible to notice over a single day. It remains invisible over a single year. Yet, over decades, centuries and millennia, it transforms continents. The Cocos Plate advances towards southern Mexico at roughly several inches or several centimeters per year. Although that rate may seem insignificant, the motion never truly stops. Day after day, year after year, century after century, the plate attempts to descend beneath the continent. If the boundary moved freely all the time, earthquakes would be relatively small. Instead, friction changes everything. The two plates do not simply glide smoothly across one another. Their surfaces are rough, fractured and irregular. Ancient volcanic rocks, sediments scraped from the ocean floor, underwater mountains and countless geological features create enormous resistance where the plates meet. Scientists describe many portions of this interface as locked. A locked fault is exactly what its name suggests. Instead of allowing continuous movement, friction temporarily prevents motion. Even though the plates continue trying to move, the boundary remains stuck. Since the plates cannot stop moving altogether, they begin storing elastic strain. An everyday analogy helps explain this process. Imagine pressing steadily against a heavy spring attached to a wall. At first, nothing seems to happen. Yet the spring stores more and more energy as compression increases. Eventually, the force exceeds the resistance holding everything in place. The spring snaps forward almost instantly. A megathrust earthquake follows a remarkably similar principle. For years or centuries, the plates remain locked while tectonic forces continue pushing against the boundary. The rocks deform slowly under increasing stress. Their shape changes almost invisibly as elastic energy accumulates throughout enormous volumes of crust. Eventually, the rocks reach their mechanical limit. Friction can no longer resist the accumulated stress. Failure begins. Once rupture starts, the process unfolds at extraordinary speed. The fault does not fail everywhere simultaneously. Instead, rupture begins at one location, known as the hypocenter, then propagates across the fault surface much like a rapidly opening zipper. As the rupture front advances, sections of the fault that remained locked for decades or centuries suddenly slip by several feet or several meters within seconds. That abrupt movement releases the stored elastic energy in multiple forms. Some becomes seismic waves that race through Earth's interior. Some becomes permanent displacement of the crust. Some becomes heat generated by friction. Some continues driving additional rupture farther along the fault. The balance among those forms determines everything people later observe, from shaking intensity to aftershock patterns and tsunami generation. By the time the rupture reached its maximum extent off Chiapas, an enormous section of the plate interface had slipped. Although researchers continue refining finite fault models using global seismic records, coastal global positioning system stations, and satellite radar observations, early analyses already revealed an important conclusion. The rupture occupied only part of the Chiapas segment of the Middle America Trench. That finding carries implications extending far beyond the earthquake itself. Large subduction zones are not continuous fault surfaces that always rupture from one end to the other. Instead, they consist of numerous segments with different frictional properties, rock compositions, fluid pressures, temperatures, and geological histories. Some segments rupture frequently through moderate earthquakes. Others remain locked for centuries before producing giant megathrust events. Understanding exactly which portion failed during the July earthquake, therefore, became one of the highest priorities for researchers around the world. Every new earthquake provides another opportunity to improve our understanding of where stress has been released and where stress continues accumulating. That distinction may eventually prove even more important than the magnitude itself. Because in the world of megathrust earthquakes, silence is often the most closely watched signal of all. The strongest shaking lasted less than a minute. Understanding exactly what had happened beneath the Pacific Ocean would take far longer. Because the rupture occurred along a shallow section of the plate boundary beneath the Pacific Ocean, tsunami warning centers treated the event seriously from the outset. Alerts were issued along approximately 186 miles, or 300 kilometers, of the Pacific coastline of southern Mexico and neighboring Guatemala. Emergency managers knew that even a moderate amount of vertical movement of the seafloor had the potential to generate dangerous waves close to the source. Attention quickly turned toward coastal tide gauges. If a significant tsunami had formed, those instruments would record the changing sea level almost immediately. Every new observation helped scientists determine whether the rupture had displaced enough seawater to pose a continuing threat. As the measurements arrived, the outlook steadily improved. Rather than producing large destructive waves, the tsunami remained relatively modest. Tide gauges near Chiapas and Puerto Madero recorded waves of roughly 1 foot, or about 0 3/10 of a meter, while little significant tsunami activity was detected elsewhere along the Pacific coast. With each passing hour, confidence increased that the rupture had not displaced a sufficiently large section of the seafloor to generate an ocean-wide tsunami. The warnings were gradually lifted as observations confirmed the limited size of the waves. The earthquake itself followed a similar pattern. Despite the powerful shaking experienced along parts of the Chiapas coast, the consequences proved far less severe than many had feared during the first few minutes after the rupture. Reports indicated that 2 people sustained injuries, but no fatalities were recorded. Some buildings developed structural cracks, isolated walls collapsed, and several gas leaks required emergency response. Across the border in Guatemala, authorities reported small landslides and carried out precautionary evacuations, including the temporary closure of schools. Considering the size of the earthquake, the outcome was remarkably restrained. Scientists believe several factors contributed to that result. Although the earthquake was shallow enough to generate intense shaking near the coast, the rupture itself remained relatively compact. Instead of breaking an exceptionally long section of the subduction zone, the fault released its energy across a more limited area. The strongest shaking, therefore, remained concentrated near the source, rather than extending across a much broader portion of southern Mexico. Likewise, the limited rupture dimensions helped explain why the tsunami remained modest despite the earthquake occurring offshore. One of the biggest misconceptions that appears after every major earthquake is the belief that a large event somehow signals that the entire planet is becoming more seismically active. The numbers tell a more interesting story. That distinction became especially important as speculation began spreading online only hours after the earthquake. Some claims suggested that the Chiapas rupture had somehow increased the likelihood of a major earthquake in California. Current scientific evidence does not support that conclusion. Large earthquakes permanently redistribute stress, but those changes are strongest close to the rupture itself. Known as static stress changes, they decrease rapidly with distance. The 17th of July rupture occurred more than 1,500 miles, or over 2,400 kilometers, from Southern California. At that distance, the permanent stress transferred by the earthquake becomes extremely small compared with the enormous tectonic forces already acting on California's fault systems. More importantly, the 2 regions belong to fundamentally different tectonic environments. Southern Mexico is dominated by subduction, where one tectonic plate descends beneath another. California, by contrast, is controlled primarily by the San Andreas fault system, a transform boundary where the Pacific plate and North American plate slide horizontally past one another. The forces driving those faults are different, the fault geometries are different, and the accumulated strain develops independently. Researchers therefore regard the Chiapas earthquake and the San Andreas fault as separate tectonic systems rather than parts of a single connected earthquake sequence. The same conclusion applies to another fault system that frequently appears in public discussion whenever a major subduction earthquake occurs: the Cascadia Subduction Zone. Stretching from northern California through Oregon, Washington, and into British Columbia, Cascadia represents one of the world's most closely monitored megathrust faults. Like the Middle America Trench, it involves an oceanic plate descending beneath North America. Yet the similarities largely end there. Cascadia is driven by the Juan de Fuca plate rather than the Cocos plate. It has its own rupture history, its own pattern of plate coupling, and its own long-term earthquake cycle. While seismic waves from the Chiapas earthquake travelled through North America and were recorded by instruments across the continent, those passing waves did not permanently increase the tectonic loading already accumulating along Cascadia. Scientists therefore continue evaluating Cascadia based on its own geological evidence, rather than on earthquakes occurring thousands of miles or thousands of kilometers away. Attention instead remains focused much closer to the 17th of July rupture. As finite fault models improved during the days following the earthquake, they consistently indicated that only one portion of the Chiapas segment had slipped. Neighbouring sections of the Middle America Trench showed little evidence of participating in the rupture. That finding immediately shifted scientific attention toward the locked segments surrounding the newly ruptured fault. One of the most closely watched lies immediately northwest of the 17th of July rupture, extending toward the Gulf of Tehuantepec. For decades, geologists have referred to this region as the Tehuantepec seismic gap because it has gone unusually long without experiencing the kind of giant megathrust earthquake expected for an actively converging plate boundary. Geological records, historical earthquakes, and modern geodetic measurements all suggest that substantial tectonic strain continues accumulating there. A seismic gap does not guarantee that a major earthquake is imminent. Instead, it identifies a portion of a fault where relatively little recent rupture has occurred despite continuous plate motion. The Cocos Plate continues converging beneath southern Mexico at approximately 2½ inches, or about 64 millimeters, every year. Where the fault remains strongly locked, that motion cannot be accommodated by steady sliding. Instead, elastic strain continues accumulating within the surrounding rocks. Some computer models indicate that parts of the Tehuantepec Gap may be capable of generating a megathrust earthquake exceeding magnitude 8 if enough of the locked interface ruptures during a future event. Although the timing of such an earthquake cannot be predicted, the region remains among the highest priorities for ongoing monitoring. Scientists are also carefully examining the broader Oaxaca Subduction Zone. The Oaxaca coast has experienced destructive earthquakes throughout recorded history, reflecting its position along one of the most active sections of the Middle America Trench. While different portions of the Oaxaca interface rupture at different times, geodetic observations continue identifying areas where strong mechanical coupling persists between the Cocos Plate and the overriding North American Plate. Those locked patches remain capable of storing tectonic strain for many decades before eventually releasing it through another large megathrust earthquake. Attention does not end at Mexico's southern border. Farther southeast, where the Middle America Trench continues beneath Guatemala and toward El Salvador, researchers are observing another region that has attracted increasing scientific interest. The Guatemala-El Salvador segment has not experienced a giant megathrust rupture for many decades. Measurements from continuous global positioning system stations indicate that significant portions of the plate boundary remain strongly coupled, meaning the plates continue resisting motion rather than sliding freely. To earthquake scientists, strong plate coupling is one of the clearest indicators that elastic strain is continuing to accumulate. It does not reveal when a future rupture will occur. It does reveal where the tectonic system is storing energy. For that reason, many recent plate-locking models display several intensely locked patches immediately northwest and southeast of the 17th of July rupture. The earthquake released strain from one section of the fault, but neighbouring regions remain largely unchanged, continuing to store energy as the Cocos Plate relentlessly descends beneath southern Mexico and Central America. This is why researchers often describe the Chiapas earthquake as a partial stress release rather than a complete unloading of the subduction zone.